Okay guys, so we're going to be going over module 9 today, which is broken apart into 3 parts: the reaction quotient, the Chatelier's principle, and Bronsted and bases. The first thing we're going to be going over is the reaction quotient. Which in this case is also known as Q. And the bare bones formula for Q is products. Oh, shoot. Oh well. Over reactants. Which, if it looks familiar, it should, because it's essentially the same formula as K, because this is also products over reactants. Yeah. So the only difference here is that, as we went over last week, well, 2 weeks ago, oh my god, it's been a while, or 3 weeks, okay, whatever, my bad, is that this is at equilibrium, and this is at any point in time that is not equilibrium. So as we went over last week, equilibrium is when your rates of products being formed is the same as reactants being depleted, right? So everything wants to be in equilibrium. It's kind of like its homeostasis. It doesn't want to move away from that. So every time that it's not at equilibrium, like in Q's case, it's going to want to shift to go to K, which is equilibrium, which means that there's going to be a relationship between Q and K. So take, for instance, if your Q is less than K, then your reaction is going to essentially shift to the right. And if Q is equal to K, then your reaction is going to stay the same because it is at equilibrium if your Q is equal to K. And if your Q is greater than K, then it's going to shift to the left. Which also, like, a little trick for this so that you're not like, oh my god, I don't remember how it works. It's kind of like I draw this as a Pac-Man, and Pac-Man's moving to eat that, and Pac-Man's going to move to the right to eat it, whereas in this case, Pac-Man's going to move to the left, and if they're equal to each other, like I said, it won't change because they're equal to each other. Right, so let me keep that there. We can do an example problem real quick, which, like I said, it's just comparing your Q to your K to see which one's larger and or smaller or equal to it. So then let's take, for instance, the generic equation 3A gas plus B2 gas yields C gas. And your K is 3.2. And we're going to determine which way the equilibrium would shift and which concentrations are going to decrease and which ones are going to increase, given that the concentration of A at a certain time is 0.5 molar, the concentration of B is 1.3 molar, and the concentration of C is 0.4 molar. So we're going to write our Q expression, which is our products, C, over our reactants, A cubed times B. So then we're going to put this in as 0.4 over 0.5 cubed times 1.3, and we should get 2.46, which in this case 2.46 is less than K, right? Which is 3.2. My bad, I forgot to write that down. So because our Q is smaller than K, it means we're going to shift to the right. So it's going to be a shift to the right, which, okay, for your guys' homework, it's okay if you just write shift and then put the arrow pointing that way, because that's usually how I write it, because I struggle with my left from my right, which is something else entirely. But okay, since we're shifting to the right, that means that we're going to try to create more products, right? So that means that our concentration of products will increase, whereas our concentration of reactants will decrease, right? So I'm hoping that makes sense. So then let's do another example. I'm going to erase this because you guys can actually pause me if you need to see the work now. Woo. Okay, cool. So then let's do another example real quick. So then once again, we're just going to have our generic expression 2A gas plus the gas yield. I shouldn't have erased the expression, but it's too late now. 2C gas, where our K is equal to 7 times 10 to the negative 6. And then given initially, the pressure of A is 0.8 atm. The pressure of B is 0.02 atm. And the pressure of C is 0.002 atm. So this is, remember last week with our Kc was for concentration and Kp was for purely gases. So this is all gases, so we can just write Qp also is equal to our products, which is C squared over A squared times B, right? So then we plug in our work, 0.002 squared over 0.8 squared times 0.02, right? Yes. So then we plug that in and we should get 3.125 times 10 to the negative 4, which in this case, again, our Q is greater than K, so we would shift whoops, not again, but okay, anyway, yeah. So we would shift left in this case, because it's greater than. Our last problem was less than, my bad. But yeah, so then in this case, since we're shifting to the right, that means that we're making more products, which we're making more reactants. Oh my god, yeah. So we're going to be shifting this way. So we're making more reactants, so our reactants would increase and our products would decrease in concentration. So yeah, that's basically the reaction quotient. It is essentially like you're doing K all over again. It's just that, as I stated before, Q is not at equilibrium, whereas K is, and everything wants to be at equilibrium because that's its most stable state. So it's going to want to shift to fix itself to go back to equilibrium, which is why we have these relationships right here. That was an ugly thing, so yeah. That's why we have these relationships, just because everything wants to be back at equilibrium.